Again, I've sort of talked about this both in this lecture and in previous lectures, but I just want to make it a little more explicit. When we're talking about statistics, when we're going from sort of the discussion of probability to statistics, we really need to keep two notions of the random variable in our head simultaneously. We need to think of random variables as this mathematical construct that I introduced several weeks ago. Okay? So a function from the sample space to the real numbers. And we also have to think of it as a stochastic object that can, quote, take on different realizations with different probabilities. Okay? And so we use, and I've been sort of consistent throughout using the notation capital X to stand for the random variable and little x to stand for the realization or possible realizations of the random variables. And I'll continue using that notation. Okay? Second of all, we've got to think of a random sample. We've got to keep these two notions of a random variable in our mind at the same time, and we also have to keep two notions of a random sample in our mind at the same time. So we think of it as an IID collection of random variables, but we can also think of we also can call the realizations of those random variables a random sample. Okay? So a random sample can refer to the random variables. It can refer to the realizations of the random variables. Okay? And sometimes we just call that data instead of realizations of random variables, and that's fine too.
How do you define the stochastic object in the process?
Yeah, I'm not going to give you a formal definition of it. This is just meant as, so the question is how do I define a stochastic object or a stochastic process or something?
Process.
Yes, yeah. So I'm not going to give you a formal definition, and the idea here is that I just want you to have these two notions of, in your mind simultaneously, that there's sort of a mathematical construct called a random variable, but then the random variable, the reason why we have the mathematical construct is there are these sort of uncertain events that happen, or stochastic events that happen in the real world, and we want to have some model of them. And so we think of it as a mathematical construct. We also think of it as a model of stochastic, occurrences or something like that. Okay, does that help? Somewhat? Okay, yeah.
Just to summarize, so we have a random sample and we create a function based on those, and that acts as an estimator which will help us to find the parameters of the...
You've got it. You've got it. That's exactly right. And we'll see, we'll sort of see examples as we go further that I think will clarify that even more. Okay? Oh, so actually, I think you just predicted what I was going to put on the next slide, or what I put on the next slide. So we know or assume that a set of random variables, a random sample, is distributed, say, IID normal, or IID uniform, or IID exponential. And then estimation is trying to determine the specific mu and sigma squared, or the specific A and B, or the specific lambda. Okay?
There will always be an error because the sample size is not infinite, so there will be error in the estimation.
Yep. And the way that we quantify the uncertainty of our estimate is through, and we'll get to this more specifically, the way we quantify it is through the variance of the distribution of our estimator. Okay? Okay. So I think we've covered this. Might choose a function. Okay, maybe I should actually sort of go through this a little bit. I think we've essentially covered it. So when I said that an estimator was a specific function of the random sample that was going to be useful for us to try to give us information about an unknown parameter, for instance. And so maybe what we do is we could choose a function whose result, when applied to a random sample, is a random variable that has a very tight distribution around the mean of the distribution of those random variables. Okay? And so if we have an estimator, a function of random variables, that's very tightly distributed around the mean, and we don't know the mean, well, that, if we get a realization from that estimator, then that's going to give us important information about where the mean is. Okay? So,
when we don't know the mean, then how can we say that the estimator is tightly around the mean?
no, we can't say the estimator. We can say analytically, mathematically, we know it has to be tightly distributed around the mean. And so what we do is we take a specific random sample, we plug it into that function that's the estimator. The estimator gives us a value, and we know that value is a realization from that distribution that's tightly distributed around the mean. So let me, maybe drawing a picture would help. So let's suppose we have a random sample from this distribution. Okay? This distribution has a mean, mu. We don't know what it is. We want to know what it is. So what do? We gather a random sample from this distribution. So it's just a bunch of realizations from this distribution. Okay? So they're both, well, I should say they're both random variables that have this distribution, and the data is the sort of realizations associated with that. Okay, so we gather that random sample. We plug that random sample into this particular function, x bar, which is equal to 1 over n times the sum of the x's. We know analytically that this thing here has a distribution that looks like this. Okay, maybe that's a little exaggerated, but basically this thing here has a distribution. We know if this sample size is big enough, this is going to be approximately normal. I'll put an A here for approximate. And it's going to have mean mu, and it's going to have variance sigma squared over n, right? Central limit theorem, well, we knew this part and this part before the central limit theorem told us this part. Okay? So this is now how this distribution, how the sample mean is distributed. So if we get a realization from this distribution, then we're pretty sure that that realization is somewhere close to this unknown mean. Okay? Because this distribution is tight around this unknown mean. And that's the, that's the sort of fundamental idea. Okay? So, one thing I do want to point out on here is that just like we use the term random sample to refer both to the set of random variables and to the set of the realizations associated with them, we use theta hat to stand for both an estimator, which is the function of random variables, and the estimate coming out of that estimator, which is what you get when you plug in the realizations into the estimator. Okay? So again, statistics does not make a, sort of a distinction between the estimate and the estimator typically in the notation.